Away we go.
Right, well, welcome all, and it's a huge pleasure to welcome David Grier to our seminar series. David's speaking to us from Washington, DC, as many of you will have heard. David's a distinguished historian of computing, as well as being in the real world, and my knowledge of historians informs me that this is an unusual combination. David is technology principal at JAGI, which is an international consulting firm in Washington, DC, and is the author of When Computers Were Human, which is a wonderful book on modern computing prehistory that was published in 2005. David is an IEEE fellow and has served as president of the IEEE Computer Society. He serves as editor-in-chief of Computer, as editor-in-chief of Annals of the History of Computing, as many of us will know, as editor-columnist for Consumer Electronics magazine and the communications of the Chinese Computing Federation. David's going to tell us about how Arpa built a global network without the benefit of a global network, something of a paradox. Thank you. Over to you, David.
Well, thank you. And I need to, and what did I just push? I have this feeling I pushed the wrong button. I'm trying to share my screen because I have slides.
At the bottom of your screen.
Yes. Are you seeing something that looks like slides?
Yes. You're excellent, David. Ready to go.
Excellent. Thank you, Doran. I sort of feel I should be introducing you as the distinguished historian of computing. Because you not only have researched it, you have built it. And I've always been very impressed with that. I also discovered as I was sitting there that I am going to be talking on a subject today, Arpanet and software engineering, quoting someone who's in the audience. I saw you out there, Brian. And that is always a little bit of trepidation when you do that. I have been working on the study of Arpanet, as I often do, because of an opportunity. I discovered that I live nearby Steve Crocker, who is one of the people who worked on the original Arpanet network working group, the original engineering team. And pioneers are rare to come across, but they're lovely because they often have access to stuff that you can't get, and especially over the last year when we haven't been able to go to archives or to libraries or anything else, having him be able to call up, email his buddies and say, do any of you have this, has been fascinating. And also, it's been great to be able to present him with documents and say, what is this? And you get the entire administrative procedure behind it, which gives great insight into how things are built, which is really the question I'm interested in, how things are built. What are the processes and procedures that we use, and how do those affect what we do? And in particular, I've been intrigued with Arpanet for a number of reasons. First, as the starting point of, I'm sharing a screen. There we go. As the starting point, or an important starting point of internet, but also as an example of the nature of the field of computing. Where does that field get its ideas? In particular, how does the field of software engineering get its ideas? Many of you knew Mike Mahoney, the Princeton historian of computing. And he argued for a long, long time before his passing that understanding software engineering in many ways is the key to understanding the field of computing once it breaks the bands of dealing solely with physical objects. And this problem of where it gets its ideas is interesting because at some level, you can view it as a variation of the physical symbol system hypothesis, that somehow there's a system of symbols that provides all the ideas for creating software, for organizing people, for using software to engage the larger world. And there are obvious questions that immediately start flowing from that. How much do the problems that you're dealing with affect it? How do the tools that you use affect your ideas for creating software? And those have been things that I have been looking at and considering for quite some time when this opportunity came on. Now, I can throw this picture up. I've thrown it up in America several times and you get this blank look. But this issue of science and management sort of combining as part of the engineering process is just fascinating. And in particular, since I spent a good share of my career as an administrator of scientists at universities, as a dean, and as a professor. I've just been fascinated with the different examples that shaped engineering practice. And one is obviously the Kinderdijk in the Netherlands, because it's, for civil engineering, it's the classic example. So much literature points back to it. When they built it in the 17th century, the science was largely known. I mean, the pumps they used were Archimedean screws, and so those go back to classic era. The windmills, while not built on this scale, existed in a variety of forms as vernacular architecture in the Netherlands. The systems for sort of putting them together in management were, again, mostly known. The governance was really novel because it required a group of people to get together with overlapping claims of land to cooperate and build the system of windmills and pumps to clean it out. So you're taking classic science systems that were new-ish but still had classic roots, a new governance and a new financing model that required complete cooperation in order to make it work. It wasn't good enough to be 90% correct. One failure could flood the whole area. And they point to that time and time again, and has gotten me to thinking, and here is where I get to cite Brian. I've not been exactly clear where you are in this picture, sir. I suspect you're there. The connection between Arpanet and the start of software engineering, we commonly date start to the October 68 NATO conference on software. If you look through the transcript, which I have done in depth, that Brian wrote, you discover that the problems that they're looking at are primarily error-free software, trying to identify and correct errors correctly, and cost. And cost, of course, is related to timely delivery. And a very common view, certainly in American historians, is that that initiates the software industry. And it's certainly true that it's tightly linked to it, but there is a broader story going on in other ways. The big one is the IBM unbundling. 68 also marks the time when IBM, more or less at gunpoint, said that it would start charging for software. It would not provide software free or wrapped into, depending on how you want to look at it, wrapped into the cost of renting a system. It encouraged a large number of people, many of whom were IBM employees, to break out and form computer software companies. It converted a number of other firms that were providing computing services, if you will, the really early cloud computing services, to jump into software. And as you read the record of that, and Bert Grad at the Computer History Museum has been very active in trying to develop that, it's an interesting problem of reducing labor costs. And in fact, you're trying to amortize software across multiple sites. And how you do that and do it in a way that produces quality work and maintainable work is a really interesting problem. And that drives, certainly from the American point of view, the software engineering world almost as much as the Garmisch conference. 3 days ago, I discovered this guy. And so this is a brand new slide. There were a number of people who were thinking about software engineering well before the 68 conference. And I think it's important to understand them to, again, to put the ARPA work in context, because ARPA is a 68 process. The development process runs from vaguely 67, is in full swing by 68. The hard work is done in 69, and they're debugging at 70 through 71. This is a man named E.E. David, who is a Bell Labs engineer. He ends up being a science advisor to Nixon, and at some level gets to be the claimant of the first high-level computer science advisor. He's an electrical engineer and a communications engineer, but he was very interested in the software development process, and I discovered, much to my surprise, took place at the Garmisch process. He argued for a long, long time that software development had a three-part process: research, which he defined as finding information you didn't know and needed to know to make your system; development, which we would now call uh, both getting the requirements process set up, seeing what you needed to do in the software, and doing a design for it. If you read his writings, those two things are very clearly lumped together. And then production, which he describes mostly as coding with, as I think a lot of people at the time did, a brief reference to testing. The growth of testing as an important idea clearly comes in the next decade. And this three-part process you start seeing echoed in the thinking of people who are producing systems, at least in the United States during this period. Now, part of this, they were clearly addressing one problem and they were not thinking much beyond it. They were thinking of writing complex systems for a common environment. And again, the unbundling is important because the 360 is at this point and for the next 15 years through 85 or 86, so maybe almost 20 years, is the dominant installed base. So that gives you a common market that you can work for. They were also talking about a very narrow process. And it's odd that Esker Dijkstra of the Netherlands was talking about this a lot, that they were looking for a very stratified labor structure with few leaders, a lot of coders who had considerably less knowledge than the leaders who were designing the software, and a limited connection of knowledge at the site, at the consumer. And you start looking at this and you start seeing, 40 years hence, when the agile crowd, the lean crowd, the extreme crowd start coming in and start changing that model. And one of the things that's, of course, very interesting about it in thinking of this as an engineering process and thinking about this as something within the context of engineering ideas, that stratified labor process was identified by Charles Babbage. It's chapter 22 of The Economy of Machines and Manufacturing. And he argues that it's the structure to do for building large systems. He was talking in that about how do you build a system to produce the nautical almanac tables, because it minimizes labor cost. And that's the process that they were working on, and that very much shapes the thinking. Many of you, I know, will be familiar with this book. It's Fred Brooks's Mythical Man Month. And if I can just throw in a personal story here, I had been president of the Computer Society about 3 days when I was at the time a dean of, guess I was still dean of engineering. I've had a dean in liberal arts, dean of engineering, and a dean of international affairs. But I was a dean, and my assistant stuck his head in and said, "There's a Dr. Brooks who wants to talk to you." And I had no idea that this call was coming. And I said, "Okay," going down my list of faculty. "What department is he in again?" He says, "No, this is a long distance call." He says his name is Frederick Brooks. And I thought, oh my God. And immediately ran, picked up the phone, and he starts barking at me. And he had certain things that he wants to do. And it was like an assumption, you know who I am. This is what I want. Off we go. Gave me the list, hung up, and there we are. And of course, as president of Computer Society, you were going to take a call from the designer of OS 360. He defined a concept of a surgical type team in his book, Mythical Man Month. That idea has influenced our thoughts on software engineering ever since. Large aspects of what he defines are still used in modified terms. His ideas are still given lip service around it, although we've moved on. He foresaw, but didn't quite articulate, the idea that we would be building systems and that quality assurance, quality control would be important, and that we would borrow ideas quite heavily from the literature of the 1930s on manufacturing, that the manufacturing mode of engineering would be very, very important to us. And this led to an incredible surge in the development of software standards and a view that said they were the core of software engineering. I think the most initial one, IEEE 370 on the software lifecycle, kicks it off. The floating point standard, which is a little bit later in the early 80s, is important. And this is a mindset that lasted for almost 20 years. It starts to kind of break up with the Agile crowd in the 90s. It also brought an interest in libraries. McElroy, who's another Bell Labs person, argued that we should be making interchangeable parts, which is again a manufacturing idea. And when he describes his ideas for having interchangeable pieces of software, he is using language and citing ideas that come from the standard manufacturing ideas of the time that had been developed for a period roughly 150 years before. So that was clearly an idea that moved it in. But these ideas, certainly in American academic institutions, and I have included one UK institution in this, seem to take a limited interest in this model. You don't see a lot of professors engaged in the conferences and discussions of this. They're pursuing a version of software engineering that's closer to a product engineering rather than manufacturing engineering. The major leaders in the US are found in 4 schools. Massachusetts Institute of Technology, which is the dominant one. It's clearly the one that is setting the standard. University of Michigan, which has a strong manufacturing engineering base, but went in a different direction. And the interesting addition to it is Carnegie Mellon, which in the United States is a dominant leader at the moment in software engineering, and arguably the world. It's one of the top 2 or 3 software engineering centers in the world. And at the time was much more interested, and this is a picture of Shannon's software engineer, computer program that he developed there with Herb Simon working on it. They were interested in, how do you shape the product? How do you shape the software itself? And were very interested in this research behind the product. They were arguing that getting that under control would help speed it along. They build on McElroy's ideas a little bit, and this is Parnasse and others, the information hiding, the black boxing, that became a very standard part of software engineering. This idea is seen most clearly in one of the big academic projects of the early 60s, which is the compatible time sharing system. And I've come to appreciate that certainly for academic computer science, and in particular the software side of it, this is a very important project. It sets the standards for so many things. The people who worked on it, even for a short period of time, went out and duplicated the kind of structure that they set up here. They were working again on a single system a complex system for a single site. They were building a time-sharing operating system, ultimately for an IBM 7090. They viewed themselves as experts writing systems for experts. And that led to certain kinds of decisions. They got a fairly small team who were working on the core services. And those would be things like the scheduler for it, the basic libraries of systems behind it, what we would call the basic shell. And they focused on the core, and then they spread out and tried to engage others, at the time solely from MIT, but as they went on from a bigger and bigger community, and get those additional users to pull in ideas. There were conferences where they worked on ideas together to try to discover what needed to be done. And there was a series of documents called the CTSS Programmer Notes, which were, it was one person editing them, but lots of people were contributing, going things from I discovered how to do this on the system to I've written this little program that allows you to do this task. Can you use it for your work? And it very much set the stage for things that we see later with reusable software, with open source software, with free software. The programmer notes idea was actually borrowed from Algol, which predates it just a little bit. Peter Nauer had a series of notes that he published on Algol that for a time he turned over to IFIPS, and then he got angry at them and took them back, as I read it. That was again trying to spur up a debate and get a large community of people involved. So again, it's working with this idea of a core team and a larger group, but it's focusing attention on core functions, central functions that have to be done and have to be done well, and that the things at the fringe of it, at the outside, were done by others. Quick overview of Arpanet. It was built by a government agency, the Advanced Research Projects Agency. That agency was founded in '58, and it was direct response to Sputnik. And it was, for about 2 years, our space agency before our political leaders got touchy about that and decided they had to have a civilian agency to run it. It thrashed about for a little bit about what to do, but in '62, one of the ideas that it decided to focus on was, in effect, building a body of knowledge for computer science that could be used for government systems. The government had built a half dozen large networked or quasi-networked systems that had all cost far too much, run over budget, substantially delivered late, and didn't do what they'd promised. And there was a feeling within the government technology circle that we had to get the knowledge base right, again, focusing on research. It is a direct precursor of the internet. The people who built it went on to be the people who helped found the internet. The technology, in particular, the TCP protocol, was developed during this period, and it was not used on Arpanet until very late in the Arpanet's life. It ends in '82. Arpanet is just a network. It's not a network of networks, but you see the elements going out. And the governance that they had, the way that they structured it and brought the people together, very much presaged how the internet would work. This is a map of Arpanet as it operated in, I would date that to roughly June of '70. As you see, there's a Boston core, MIT, BBN, who built the routers, and Harvard. There is a California core, which was UCLA, RAND Corporation, Systems Development Corporation, the University of California at Berkeley. Surprisingly, not Stanford, but SRI, Stanford Research Institute. The one interesting little anomaly is Utah. That's in there for a couple of reasons. There was a personal connection of someone who had been at Stanford and who wanted to be back in Utah, who came from a Utah family. And if you've spent time out there, it's a very strong, tight community with a lot of family ties. And also because they wanted to have 4 initial sites, UCLA, SRI, SDC, and a site out of state so that they would be running across a state border with telephone lines to see how that worked. And Utah was close enough to be able to do it. This is, of course, quite a different problem than what was being posited for the software industry. It was experts writing for experts. It was a heterogeneous environment. And in particular, the documents from the early stages of the network have a couple phrases that are notable. The one I like is any commonality should be considered happenstance. The idea that the researchers would set up their own computers, they might alter the software radically, that you couldn't expect anything to be the same. And in fact, nothing was. Of the initial 14 sites, they ranged from computers that represented characters with 6 bytes, with 7, with 8, and with 9. They had a variety of operating systems. Some were commercial, most were homegrown. All were time shared, and that was very clearly in the initial documents, that they were expanding time sharing with network connectivity. It was also not a large software system. The early documents speculate, as they're preparing, that they can write most of their software, which consists of modifications to the operating system and a few small standalone programs, in less than 16 kilobytes of code. They're using word metrics at this point. And there would be multiple versions of basically identical code, or of a single code, if you will. I've done a little bit of plowing through the pieces of code that exist out on BitSavers. And it's clear that there are at least, if we call it an architecture, 3, maybe 4 different architectures of the code that is installed. And then the key part that they wanted to add, they wanted these small systems to do, is like CTSS, be extensible. They wanted people who were not part of the inner core to be able to extend it without modifying that inner core. The engineering influences on it, the direct engineering influences, are interesting but limited. When I started work on it, sat down with Steve and said, "How much did you know about the Garmisch conference?" And he looked at me and said, "What was that?" I said, "You know, the NATO conference on software engineering." Shook his head and said, "Never heard of it." And Steve goes on to be be a program leader in Arpa and be in charge of their software engineering work. And I found it interesting that that was it. I laid out the people who were there, and he said, he's sort of put his hand on the table and said, "You have to understand, no one involved in the software engineering community was involved." That led to an interesting story, because he said that the software work on the Arpanet began in August '68 at a meeting that he attended, Vince Cerf attended, several of the other Arpanet pioneers, at the University of California, Santa Barbara. That's where it began. And I start poking around, and I eventually find a copy of the minutes of that meeting. Didn't expect to quite find that, but I got it. And I presented it to him, and he goes, "Yeah, this is great. This is exactly what, these are the people who were here. This is the notes of the first meeting." And I said, "Problem with that conclusion, Steve?" He said, "What?" "Notice the last line of the note. The minutes of the prior meeting were read," it says. "There was a prior meeting," he said. "No, there wasn't, but you read the minutes." "Well, I don't remember that." And of course, 60 years on, it's not necessarily that you're going to remember every detail. But as he started thinking about it, all of a sudden it dawned on him what was going on. He goes, "Yeah, I guess there was some prior work on this." He's been very good about modifying his ideas, as we have found documents. And then I said, "One more problem, Steve. Look at the list of attendees." He goes ticking down. Yep. "Look who represents System Development Corps. Barry Boehm, one of the big, leaders of software engineering in the 70s and 80s. He was primarily software economic modeling." And he sat there, and I said, "I guess he was there. Let me see if I can find him." And this is why it's great working with pioneers. Spends a little time Googling, finds him, email goes back and forth, and we have a discussion about his role in this. Barry was involved in the SDC large system development and was considered an expert in large system development at the time. And he was there to look and see what these people were doing and see what he could add. He remembers adding little. Steve remembers adding little, but he was there, and that's part of the connection. The more intriguing question is someone who falls a little bit out of academic software engineering is Melvin Conway. Melvin Conway wrote an article, "How Do Committees Invent?" And he said that software design is identical to your division of labor. Once you've made the assignments of people, that's what your software design is going to be, or vice versa. And this is his article, "Do Committees Invent?" It was in Datamation, had a lot of circulation at the time. Particularly, I remember my father having a copy of it. It's contemporaneous. There are a whole bunch of problems in trying to say that how the team was arranged is reflected in the software. And first off, the problems are, there's some problems in what forces the division of labor. The team ends up being largely young graduate students and contractors separated by hundreds of miles. Arpanet was built with the Postal Service. They send letters back and forth with stamps on them to share their ideas. And the question becomes, how much was it shaped by that fact? And it's tough for me to see that. They're certainly responding to the computing environment. They're certainly responding to the problem that's put in front of them, which is to try to make a general purpose network, something that is an extension of can be an extension of any time-sharing service. And so the cause and effect issue there is really kind of intriguing, but it seems to me that this is ancillary. The fact that Arpanet was built by young men sending physical letters back and forth is interesting. It's quaint, but it's less interesting than how they were thinking about it. And this goes back to CTSS. Many of those young men had seen it, had known about it, had worked with professors who had helped develop it, because that's only 6 years before. And they are shaped by how that group attacked CTSS. Their first task is to isolate the diversity problem. And the debate at the start goes back and forth. How do we get a commonality that we can all deal with? And they were in particular looking at what are the central services, what's the minimum set of services can we do, how can we make them universal? They wanted to maximize the freedom at the nodes. And in particular, there's an interesting series of discussions within ARPA going, we can force them to build this network, but our influence is limited. We pay the bills. We are the ones financing their computers. And so we can insist that they all be connected and all have services. But they're going to end up developing the nodal services themselves. And there was a technical goal that again comes from ARPA, which is process-to-process communication. The ARPA leaders said, we want a network that can take any arbitrary process and talk with any other arbitrary process. Some of the early people on the network didn't agree to that. And they were looking at two basic things, a login and a typo on my slide, file transfer, not final transfer. Sounds somewhat ominous. Remote login to computers, being able to use something at a distance, and being able to transfer data and files back and forth to it. There's an initial amount of work done on that problem, including the very first demo, which is end of October, early November '69. There have been movies made about it. Glenn Kleinrock has been very big at promoting it. The lo and behold moment where they log in from UCLA into SRI. That's the first usage. It was a first usage focusing on remote login. They had a stronger sense of remote login working 3 months later, but it was far from universal. It required a substantial amount of modification of local operating systems and never caught on the network. But it also indicated that many of those early developers were thinking in terms of that problem, and they had to be regularly pushed into thinking about something bigger. Now, some of the isolation came from the hardware engineering. The ARPA office concluded that the only way to make this work in a diverse thing was to have a common hardware, and they devised what they called a communication subnet. That was built around a series of common processors, which they called interface message processors, or IMPs, which we would call a router. And in one of the cute little stories that came out of it, the company that built them was a Massachusetts company, BBN. As with many government contracts, the notice of the contract, defense contracts, was sent to the political leaders of the state prior to BBN getting it so that they could get some of the credit. And the senator there was Edward Kennedy, a well-known American senator. And his office misread what happened, thinking about Boston as the head of sort of the center of Irish Catholic population in the US, sent BBM a note for its congratulations on getting an interfaith processor that was clearly unifying churches, not computers. It was, in many ways, a hardware engineering problem, but a pretty minor one. It was a standard Honeywell processor. They added a little bit of new hardware to it, which were known modems, basically. They rewrote the software to handle packet switch networks. The key packet switch technology was here. One of the measures of the difficulty of the problem is that they had the hardware modified designs done in about 2 months. They had the software designed in roughly the same time between January to April, 4 months. They had defined it, and they have it operational 6 months later. And they started installing this network, and it's unused largely for a year. The ARPA office hoped to isolate all diversity in the hardware, use hardware to isolate it all, and that each site could basically tap into this common network with locally done software, and they wouldn't have to sort of unify the process. The initial work on that caused a bit of a crisis amongst the first workers when they realized that put an awful lot of responsibility not on the sending end, but the receiving end. And in some ways, it forced programmers to handle details at both ends of the communications. And that meant all programmers had to know the details of programming of two different machines. And that caused the group led by Steve to go to the Arpanet and said, why don't we just punt on this and go back and worry about remote login? The response was, no, we're not going to do that. We could get a remote login network much more cheaply than this. Go back and work. And that returns us to, this problem of a three-part process. They did not know how to make that aspect work, how to get an arbitrary process to talk to an arbitrary process. That required a great deal of thinking on their part, and it was a fairly small core group that did it. But they were all graduate students. They tended to focus on the California end because they could meet a little more easily, and their mail went faster. And they spent about 3 months arguing about it and thought that they had the basic idea, that they had figured it out. And that was involved basically pulling in a virtual circuit into the node computers, pulling it, not relying on the commonality of the communication subgroup to do it. They asked how much work was that going to take. They were beginning to realize a lot more than they anticipated. It took 2 years to make it work. And the first thing that they had to do was to sell their ideas. And that's really the end of the research phase and moving into the development phase. They had to sell the idea to all the people at all the sites. They had to identify the required services. They had to identify the issues that needed solution and start to fix the problems. And if you look on the map, that's the core group that worked on the first part. Utah, UCLA, Santa Barbara, and SRI. They introduced the idea in February 70, and it exploded. There's a pile of mail that is in many ways very cute for 3 months. And these are grad students who think they're experts. And in many ways they were. They were some of the best trained people in the country. They had very strong ideas. They had firm ideas about what should be in the system. And in particular, once the Massachusetts people started doing, they had other ideas. They were working on other systems. And they kept trying to push stuff out of the system. They were very much wanted a small part. They systematized this process in something that was very much like the CTSS programmer notes and the ALGOL notes, which they called request for comment. And the title is in no little part because the California group was a little bit scared of the Boston crowd. They kind of thought of themselves as interlopers or feared that they would be viewed as interlopers. And if they called them the standards documents or the programmers documents, they felt that they would face too much resistance from the Boston community. That's MIT, BBN, which spun out of Boston, Lincoln Labs, which spun out of MIT, Lincoln Labs, which spun out of MIT, and Harvard, which just thinks of itself as Harvard and doesn't take guff from anybody. So that process went on. There's a fairly substantial literature that compares it to a standardization process. And I think that I should also add most of this literature is talking about a little bit later chronologically. The work done in 68, 69, and 70 was clearly not one. It certainly lays the foundation for one, and the institutions they form become standards institutions. In particular, the work in 68 and 70 was not formally conducted. Several times they would stand up and say, you know what we need to do? We need to go through these steps and then have a vote, and that will be our solution. Didn't work. Every time they set that up, it failed, and it failed to get to the vote. There is another literature out there, some of which I have reviewed for the New York Times, that says it was a democratic something of the late 60s, that they were all loving each other and had group hugs and it was collaborative. It's not democratic in the least. There were people who had stronger votes than others. There were different amounts of clout, and they used it and they pushed it around. But by April, they've come up with a basic design: links, sockets, layers, the things that we know and understand about the basic elements of Arpanet. There were three problems that came out of that, and a bit of a controversy. One is that their design did not handle interrupts well. And that required a certain amount of debate. It ultimately required them to break some of the grace of their their design by going around layers, the very nice layers they were using to isolate diversity. The second part was flow control, and that was caused by the fact they had limited memory, that you couldn't send out a message and assume that the receiving computer could hold it until it needed it. That devolved into two camps that had little in common, had different goals, and had different approaches to it. And that was a very hard problem to solve. It took 9 months. And then there was a third problem. One group wanted to be able to dynamically move connections, transfer from one node to another seamlessly without the processes knowing what was going on. That met tremendous resistance from one group of the programmers. And eventually, the ARPA office, as I'll mention in a second, steps in. The interrupt, a lot of heat. And in particular, it's interesting, there's a purity of design. We need to maintain the layers. We need to isolate complexity. That was quickly resolved when a group of people said, if we provide this hook and go through the layers, we can push the issue to Telnet. Everyone bought that and said, great. Telnet being the login software. Flow control. The two versions were to have the receiving computer say, stop sending me stuff, versus the sending computer say, let me know when you want something next. That was 9 months. Again, it was memory that did it. And they had two very different goals. And they're not talking to each other, they're talking over each other. Ultimately, it's a compromise that one side wins and the other one doesn't, but the winning side made a concession to the losing side, and it required a substantial intervention by the Arpanet office. They had to come in and say, basically, we need it done, it's got to be done, this is the side that's going to win, you find a deal that makes the other people happy. And that's in many ways the last thing that was fixed before they could develop. The dynamic link problem, it really hinges on, there's a lot of research to be done here and we don't know how to do it. They tried formal debates, there's a huge stream of documents. Finally, in August, the ARPA office calls up Steve and Vint and John Postel and says, it's over, you're not going to do it. And it was sort of, what do you mean you're not going to do it? And they said, we're not going to do that. You're going to find some other way to solve your problem. And they immediately turn around and limit a certain amount of movement to the initial connection problem. And that basically gets done what they need to do. Although there are a number of them that feels that there were problems that remain to this day. The outcome was a design. It had 11 primitives, basic commands, syntax and semantics defined. This was the design. They did a sketch for the operating system software, but said it all had to be done locally. It described the protocols for using them, and it really turns the network into a network device, external device. You know, very much like a hard drive, but a hard drive that's less predictable and has more things going on in it. The diversity at this point really is handled to a limited extent here in the local implementations of the primitives and the protocols, but it pushes it to the higher level protocols. And Telnet, the login software, was the next piece of work that they did. It's done in an entirely different way. It has, instead of being done by graduate students, the leader of that part of the project was a Raytheon employee who had built a substantial network to allow Raytheon employees to dial into any one of Raytheon's many different computers, and at some level avoid having their terminal know what was going on, that it handled data changes and different protocols very seamlessly. But it's a very different kind of network and far from as flexible. That person was Thomas O'Sullivan. He, interestingly, was a psychologist and had worked with PBXs and that kind of telephone switching work to do it, to build his network. He did a survey of all equipment, built a model terminal, an artificial model terminal, mapped all the terminals from his survey in and out of it. It's a very complex problem, but it's very straightforward. It was also the first that had to be redone. His Telnet worked for about 15 months, and about 3 months in, everyone is saying, we got to redo this. There are performance problems, it doesn't support operating systems, and they were just starting to get video terminals, and his work hadn't done it. So in effect, it's redone with the same kind of engineering to get more or less what we have as the Telnet that has been with us ever since. The final stage was trying to test everything and make sure that we had a standard that allowed everyone to know that they had done it correctly. Testing became a big thing. Initially, they tried to have SDC set up a standard interface, everyone would test against it, and if you worked at SDC, it all would work. They were going to certify it, although they did not really define it well. And they very quickly discovered that that did not work. The group, being a little bit desperate, held a group meeting at MIT in October '71. And they said, we're going to talk about issues, and oh, by the way, we're going to set aside a morning for us to test all of our software end to end. We'll use one of the MIT labs. It was a 4-day conference that was supposed to be talking about the future of the network. It ended up being a 4-day conference where they did testing mostly, argued while they were testing, and had a few meetings to talk about what they would do at the next meeting. But that process got all the software working with everyone. It was an n-squared process. But it gets us back to, what does this do for software engineering? And again, there's a lot of thinking going on, and not just the usual crowd that the crowd that established, and I say that knowing Brian is out there, the crowd that laid the foundation for the mainstream push of the 70s, 80s. They're all thinking about the same issues: minimizing errors, meeting deadlines, minimizing costs, acquiring unknown knowledge. And Alan Perlis just did an awful lot of discussion about that and has a lovely essay about needing to be honest in your projections about how much you don't know. It was clearly completely untouched by unbundling, though that's a very important part in shaping the American approach. That, as I said, was a very different environment from ARPA and led to things that I think supported that key push in software engineering and helped develop in practical installation the ideas that they were doing. There were other problems, though, that needed attention, in particular this diverse environment problem. That keeps coming up again and again as they move forward, oddly pushing for more and more standardization. But the other part that is this idea of the highly skilled team. They were very proud of who they were and what their training was. And they said, we are programming for ourselves. We provide the central code. We push diversity to the fringe, innovation to the fringe, and we let others modify this to meet local needs. And in many ways, that was part of the great success of Arpanet, that they were able to do that, and that the programming that went on, ultimately there are about 128 nodes of it, was very innovative, but it was done independent of that and very free from having to worry about the core and fitting themselves in. They knew that they could go process to process. That was all that mattered, and they could work on their own problems. So can we come up with any interesting statements about the difference between those, particularly anything that helps us? Does the division of labor follow the structure of the project? Well, the answer is yes, but what does that tell us? There are divisions of labor caused by location. If you go back to the, which is again an AT&T literature, oddly, of how labor is divided on project. You have location, you have materials, you have tools, you have nature of the problem. All of those were part of it. And I'm not sure there's any single track that tells us a lot. Large business projects, does that help us any? Is there a conservative nature that they follow? They certainly felt that they were putting a great deal at risk, both money and process. And that has some interest that I think needs to be traced down. The bright grad student thesis that many have put forth, do you let them make decisions? The answer is Arpanet sometimes did and sometimes didn't. All of these things, again, point to the underlying problem, which is oddly not mentioned as much in the literature. I mean, it's sort of what Perlis is getting at. What's the risk? The risk of not knowing what you need to know, the risk of interfering with operations, the risk of having investments go bad. And you really start seeing that the ARPA office was willing to tolerate a certain amount of risk, but was also willing to intervene to minimize that risk. Who takes responsibility? In November '69, they basically said, you've got to do process to process. To the network working group, the group that were working on this. We will not accept the fact that you can't do it. They, in August '70, it's brutal the way they did it. Give up this part of it. It's over, it's done. You can't work on it. You have to work on getting the other things done and figuring out a simpler way of solving your problem. And the interesting point is that at some level scares the network working group, and they get much more focused about making decisions themselves. There's a couple intermediate things I don't discuss here, but in February '71, they have a meeting where a couple of their members stand up and say, this is what has to be done. We have to make this decision. We're willing to make it and move on. As you start going ahead to the lean agile group, the continuous delivery group, you start seeing some of the same kind of decisions being made. Minimize risk, trying to fit the problem and the division of labor and the finance and governance all into one box. There's an interesting comment that Dave Clark makes in '80, that the network was based on rough consensus and running code. That is both interesting and true and not true at once. But it does point to some of the lessons learned. Arpanet was never a consensus-based organization. They at times like to think they were, but some people had more votes than others, and there are some people whose objections didn't count. And there were times that the objections of the whole group or the majority of the group didn't count. So it's clear that the decision-making process, that the process of engineering didn't require unanimity, and also was willing to accept the fact that a decision may not have been completely made. Rough consensus not only implies not complete consensus, but some people may not completely buy into the decision. The running code is clearly important, being able to demonstrate what you have. But running code is not quite the same thing as debugged code, and certainly not the same thing as final code. And it certainly points to the fact that the CTS, Arpanet, and structure of more academic-based software engineering is not as final, not as complete, not as thoroughly done as you might do for a final project out in the commercial world. So one of the things I have been really focusing on is, again, looking at risk. There is a writer in economics, Oliver Williamson, who has a transaction cost theory that says we design our production structures to minimize the cost of production. We design our decision-making structures, our management structures, to minimize the expected cost of the transaction, and included in that expected cost is the expected risk. And that includes trying to address things of who makes the decisions, how they're made, how the decisions are assessed. In effect, where you are putting the points of risk in any organization process. And that to me seems more than anything else an interesting way of coming to grips with this and with software engineering as a whole as it emerges in the 70s and 80s. And it gets us back to, the Kinderdijk issue. The places where the decision process was made in that are become fascinating because it's something that comes out of the Holy Roman Empire. Good heavens, did no one check these slides for typos? The governance comes from the Holy Roman Empire, from the German states to the east, because a number of states had to cooperate to build this system of dikes and pumps. And yet they were not willing to take complete responsibility for the operation of it. There was an engineering, there was a civil group that is partly military again and partly civilian that is responsible for developing this system and for managing it and taking the decisions. And how does that balance of power work? How much does the engineering community get to take responsibility for what it's doing? And how much does it push back to the group that's funding and financing and providing the political framework is, to me, one of the fascinating questions of software engineering writ large. It really says, where does the technical hit the organizational? Where does the innovative part of developing new systems and new services meet with the existing business processes and the structure that we have developed for allowing the public to comment on what's happening, or the markets to comment on what's happening, or the users to comment on what's happening. And that is what I have to say, and that is what I'm working on at the moment. And if there are questions to be had, I am glad to have them. Or if you'd like to stand up and give a little speech about your experience, that would be interesting too. And you wouldn't need to pretend that it's a question.
David, thank you for a fascinating talk. I think I've invited people to indicate using chat if they would like to ask a question or make a comment, as you've suggested.
Okay, and I need to find where my chat box is then.
It's okay. I'll monitor the chat box.
Oh, excellent.
David. And
okay.
We have a question from Eric Bodger,
okay.
which came in quite early on in your talk.
Roger.
Yeah.
Roger. David, could you unshare your screen, please?
Yes, and I'm looking for where Zoom has gone so that I can do that. And I have the little box of all of you. Oh, there it is, right there. Stop share.
Great.
There we are. Yes.
I think you may be able to see the chat, David, on if you click chat. At the
if
bottom.
I click chat, yes.
Yeah. Eric Bodger asked quite early on in your talk, how much cross-fertilization was there between Arpanet and the networking of CP67 systems in the late 60s?
I really don't know the answer to that. There are several, most of the hardware engineers came from Lincoln Labs. And so there's a cross-fertilization there, but not with those systems. The one person who was most interested in seeing what other people were doing was Dave Walden, who was a BBN employee. And I would suspect there's several of you out there who know Dave. He went out and he wrote several papers on, historical networking, which went back to like 64, 3 years of it. And if there is something, it would have come through him. I've read his work and I haven't read it closely enough to have the answer to that question in thought. But he was systematically looking at it. Beyond that, institutional connections or programmer connections, I don't think there was much. A little bit with the French groups, but it seemed to go more from Arpanet out rather than into Arpanet.
David, you won't be surprised, and I think we'll all be fascinated. Someone called Brian Randall says he's
yeah, I see him
comment.
Right there.
Brian, we'd be delighted to listen to what you have to contribute.
Yes, very much so.
Well, first of all, let me say that was a great talk. I really enjoyed it. I have a number of memories. I can't guarantee their accuracy. I've found it very embarrassing sometimes going back and looking at my paperwork and realizing how inaccurate my memories are. But anyway, in no particular order of importance, I was delighted by your referring to the How Do Committees Invent paper. That certainly, the datamation paper, that certainly was very much a quoted and enjoyed item. I think at, or if not at, then certainly very shortly after the NATO conference, the first NATO conference.
It's published April 68.
Then, yes, I'm sure then it must have been talked about at the conference.
Okay.
One of the main things that I recall being in that paper, which you didn't mention, was the notion that a complex organization which builds a system will find that the structure of the organization is matched by the structure of the system. And the lovely example quoted in the paper was apocryphal, perhaps, of the small 8-person software company that got at the same time projects to build a Fortran and a COBOL compiler. They had not had much experience of either. They rapidly decided that COBOL was more complicated than Fortran. So they allocated 3 of their people to the Fortran and 5 to the COBOL, and they produced a 3-pass Fortran compiler and a 5-pass COBOL compiler.
Okay,
Right?
interesting.
I have seen things incredibly similar to that in much bigger, essentially military systems. Not that I was involved in personally myself, but in some of the MOD advisory committee work that I was involved in. But I won't go further down that.
No, but I would be interested to hear them at some point, Brian, if you would be willing to talk with me.
If you don't mind, I'll ignore that comment.
Okay.
Memories of the time of the building of Arpanet. What I recall was the great, as seen from the outside, was the great stress and emphasis on the importance of things like remote job entry and file transfer, viewed as a means of using network to help get access to resources, non-local resources. No interest at all, apparently, in something called email. Our understanding was, and you may be able to correct this, was that email was almost a skunkworks project by the National Committee of Graduate Students. And certainly it became by far the most important initial use of the networking. You mentioned Ed David. I remember Ed, and I'm pretty sure he was at the first NATO conference.
He was. You quote him in the first NATO conference.
Yeah,
yes.
he was quite influential there. Final comment that particularly at the NATO conference, in the words of some of the people there was a lot of confusion of the notion of software design and software manufacture, and people who were talking about software, but who were coming at it from a physical world rather than the software world. To my and other colleagues' mind, had got things completely wrong. Software manufacture really was duplication of files, when you'd completed the program. So the actual the analogy to the manufacture process was almost trivial. And the realization that all of the huge amount of effort was going into what in hardware terms would have been called design. That just wasn't understood, nor I think was the economic consequences of this. Certainly, I recall that was one of the sorts of issues that was reverberating around. Those are the immediate thoughts I have to your excellent talk. Thank you again.
Well, thank you, Brian. I very much appreciate your presence and your comments. I would like to explore some of them. I can add a little bit on email. Email, the network is operational in late fall of '71. But within months, people are sending messages through file transfer, and someone says, there's got to be a way we can make this easier, and they get a more systematic way of doing it. And then someone says, why don't we make an email protocol that allows us to kind of deliver it to any place based on you send it to this message, to the address. And that first primitive email, they do get a group together. Skunkwork, it was not planned, certainly, but it's one of the things that the group, you can kind of see them swing their attention going, this would be cool. And a subset of them make it work. So it's the exact, certainly was not anticipated that this was going to be an important service, but it was anticipated that that kind of development was going to happen almost instantly. And it is indeed the first one out of the box, with the possible exception of RJE. Remote job entry was something that that group resisted, and so many of them were involved in it that they had to make that work. And so that's a little bit ahead. But email, without question, you see this group going, that could be cool. Let's try it.
Thank you, David. Jorge Aponte Gomez has a couple of questions about agility. I don't know whether you'd like to say a word, Jorge?
Yes, thank you very much. It's a pleasure to be here. I was thinking in my studies in electrical engineer, and I have never heard any story like this. So thank you for the conference. It's a very nice conference. I think more people have to study these things, because past developments are the future developments. We need to address the knowledge that we have in the past. So it's a great conference.
Thank you. Thank you very much.
And I think I wish to know how the agility concept was developed in the past, and why now this concept has taken too much time to become a normal procedure.
I mean, there are two things. Agility as if you will, sort of a movement, dates itself to a couple of things, basically 99, with a group of programmers getting together and writing a document that they call the Agile Manifesto. And it's over the next couple of years, starts moving into mainstream, and it really gets adopted big time with mobile cloud computing in 2008, as I see it. However, the ideas that they were addressing had been bubbling up through the software engineering community, and you can trace the problems back to the conference Brian was talking about at Garmisch in '68. But there's a period that during the 80s and 90s where manufacturing is getting a greater emphasis on quality. There's a greater emphasis on making sure that the customer and that the specifications, the requirements are well defined, that starts becoming a key issue here. And most people trace, if you will, the start of interest in Agile in computing to a manufacturing engineering book that came out in 1989 called The Machine That Changed the World, which is about auto manufacturing and the Toyota experience in particular and how they were managing that. And that took a couple of years to convert those ideas into the world of software and computers. But it was a very influential book. And that sort of sparks it, and things move forward. And it seems very clear now that Agile is in many ways the dominant form of engineering that we see being used at the moment, or some variation, or at least what someone thinks is doing. So that's the story as I understand it. It's a common theme that got a special impetus in the 90s, and then an application, the cloud, the mobile cloud apps that could really utilize that kind of tight connection and fast turnaround.
Thank you for that. Jonathan Aylan has a question.
Yes, that's a marvelous software story, and I hugely enjoyed it. And it's caused me to think about all sorts of other large systems like Sage that were developed.
Mm-hmm.
In a way, it's Hamlet without the Prince of Denmark, because you've said nothing about hardware.
Yes, that's correct. Are you going to help? Are you going to help correct that?
No, I'm just going to ask you a question. This was the period when the telecoms people were beginning the switch from circuit switching to packet switching.
Mm-hmm.
And I'm wondering whether people like Raytheon, for example, were stuck in the circuit switching paradigm. There is a switch of paradigm here in the hardware, and how did that influence the software?
There is, and at some level, the shift is also occurring at 68. Once processors become a printing press problem, once you get a processor on a chip, that changes a whole bunch of thinking. And one of the great things which I would recommend is the issues of Computer Magazine in the 1970s. They're all in the IEEE online. Well, that's not true. There are 3 years that have some missing issues, but and I keep yelling at them. But nonetheless, one of the fascinating things is you can see the Computer Society and the IEEE changing direction in a very short course as they are going from designing their own designing architectures top down, designing instruction sets, to designing utilizations of processors. And it's a completely different way of thinking. And that happens, basically 70 to 76 roughly. And it's a fascinating process. And with it, the applications start coming, one of which is packet switching for the telecoms. For a variety of reasons in the US that are slightly different from Europe, the telecoms were slow to embrace it. They had a very large installed base of crossbar switches, and that they knew how to run them and knew how to work them, and were still wanting to get return on investment. And it took that kind of thinking about how to use these processors and use them rather than specially designed machines for it. And then the promise of fiber, which is again a late 60s thing, because the physics of fiber are now become obvious. I want to say it's 68, but it may not be exactly that year. Certainly by the early 70s, they realized that, okay, it's not going to be copper connections soon, it's going to be fiber. And when it's fiber, that's going to be a scale of magnitude that crossbar can't handle. Even if you do the right, kind of devices that convert it from light into electricity, do a crossbar switch and out. And so those things start pushing it forward. I do have a glib joke line that says, I do not believe in the physical reality of hardware. And part of that was, my father was a computer scientist and worked for the company, one of the companies that becomes Unisys. It was Burroughs Computing. And that gave me access as a kid to all sorts of stuff that that any kid now would have, but my peers didn't have. And Dad very kindly, very graciously introduced me to a lot of people, and in particular, one was a hardware designer who was convinced that I should be doing that and I should start there. And his firm was indeed very much focused on it. And I could see as a kid that I really didn't care about hardware. Software was the cool thing. And so as a 14-year-old, I started taking this attitude of I don't believe in hardware. Irritated several of Dad's friends, so that it was like the big benefit of it.
That's a very neat answer, but to what extent were these people at under the direction of Arpa influenced by the possibilities of the packet switch rather than the circuit switch?
The packet switch at ARPA, in particular, the person who is in many ways the lead designer of all this, Larry Roberts, he wanted a packet switch network. There's no question. The Department of Defense had built 4 big systems that involved networks. One was the SAGE system. One was a thing called BMUS, and it's a ballistic missile thing that I don't remember what all those things stand for. It had 4 sites, and they all fed into Colorado. It had another radar site. It's kind of the mid-Canada line, which was a string of sites, again, that all went into a single site. And then in the mid-60s, they were just putting the final touches, 3 years late, on a logistics system for the Strategic Air Command that handled, parts and personnel and where planes were and all of it. It was a logistics system. That was a network that was a square with a thing off the square. And that had run so much because the routing problem was not solved. It was not packet switched. It was fixed hardware. And everyone in the Department of Defense said, this is the stupidest system we could have bought. It locks us in with one vendor. It's not generalizable. It's terrible. And they said that internally and externally. They're saying, no, this is the best use of money that we had. And in many ways, that system, which operated with these switched lines as its core part, through the late 70s, was the one that said, we've got to find a general way. We've got to find a way to build a network that's independent of machines and uses diverse machines. So that was there. But there's a discussion to build a new network in 68 that ends up creating AutoDIN, which ends up being a switched line computer network. And that clearly goes its own path without listening to the Arpanet crowd. And it's kind of the last time that happens. So there's a great pull in here, and Larry Roberts wants to build a general purpose independent network that talks process to process, because once he has that, he can build new systems and not worry about how the networking works, because he's got a network.
Thank you for that. Tim Banks has a question about manufacturers' involvement.
Okay.
Tim Banks?
Yeah, hi, sorry, I was just coming off mute there.
Okay.
My involvement in data networking back in the 80s, I suppose, early 80s, one of the big issues was vendor interoperability.
Mm-hmm.
I mean, to what extent were the IBMs, the digital equipments and so on involved in the development of Arpanet? Because we still ended up with SNA and DECnet and all those other things.
Yeah, and DEC is always an interesting question, because in particular, DEC did not have a place at the table, but it had people who showed up at the table pretty regularly. And it's tightly connected to the Massachusetts community. And so it was there, and it marches off and goes its own way. So they were there. IBM, we've had a lot of literature on the IBM culture clash between, their very strict, rigid, sort of backward-looking researchers and executives, and how they didn't fit in with the new computer science crowd that's emerging in the 60s and 70s. To their credit, they asked if they could go to Arpanet meetings and the working group meetings and others, and regularly sent people who apparently showed up in suits and were a little bit out of place, but they were there and clearly listening. They offered a fair amount of help for integrating Arpanet into IBM 360 operating system. And the network working group were spared some of the tasks of that. But they weren't, neither of these groups were major participants. Some of the smaller computer firms were quite active, and almost all of them went bankrupt shortly thereafter. Scientific Data Systems was involved in there, clearly a difficult company, and they were bankrupt soon thereafter. They're bought out by Xerox. Xerox comes, and they're not a particularly well-managed firm either. the Intel crowd, the crowd that becomes Intel, this Fairchild at that time, they're clearly quite interested, but they're viewing it as a line down. The Cisco people, they come out of this group. Bob Metcalf is part of the Arpa crowd. So it's an interesting thing, but IBM in particular is the major one that sends, IBM and Burroughs. Burroughs built the ILIAC 4, and getting ILIAC 4 on Arpanet was an important thing. And so they sent people regularly to do it. And one of my interesting Burroughs stories at the time is shortly after they're up and running, I am a Burroughs High School intern trying to make RJE work on a bunch of their computers and struggling with it. And it's clear in hindsight, from my perspective, they were in effect going their own and not using much of this. But it's more of an observational role, I would say. I think I've run out of ideas to say.
That's great. No, thank you very much. That was interesting.
Yep. Brian Shearing's asking about high-level languages for system software. Brian.
Okay.
Thank you, Roger. Round about the mid-1970s, I found myself implementing a time-sharing system on a mini computer. Actually, it was an American mini computer, Varian Data Machines. Do you remember them? They sold quite well. They sold quite well in the UK, and they hadn't got a time-sharing system, and so we decided to write one. It was at the same time that the trend for writing system software in high-level languages was becoming quite widespread. People were writing operating systems in high-level languages, and the end product was extremely successful. And so we decided to do that. And then I hit the problem you mentioned, the one of the interrupt. I simply could not see how to construct a high-level expression of how to deal with somebody hitting the Control-C in the middle of an arbitrary calculation or computation going on. I didn't know how to solve the problem, so I phoned up Tony Hoare and said, do you know how to solve this problem? And he said, no, but we're working on it. Why don't you come to Belfast and spend some time? He hadn't gone to Oxford at that time. And so I spent a very enjoyable week in Belfast with his team, and we did figure out a way to do it. But the moral of that little story is that we were striving with using high-level languages for writing system software at that time. And I wondered what sort of software was being used on the various projects that you've described so wonderfully this afternoon.
All of the network software, it's really interesting. And again, I'm a Burroughs person, and I was teased on ALGOL. I could program ALGOL long before I hit high school. So it's a question that has interested me and has put me at interesting odds at times with the history of computing group. In 68 and 69, there is a tremendous amount of work being done on compilers and compilers and general purpose languages that leads to what you're talking about in the 70s. The Arpanet crowd did not use them. All of their things are written in assembler at a fairly conventional level for the time. The Control-C problem that you mentioned, as I said, I was teased on Burroughs. The Burroughs B5000 operating system was written in ALGOL, and the people who wrote it were led, I would say, led and directed by a bunch of CTSS alums. And the ALGOL they used was Burroughs ALGOL, which is not ALGOL 60, but close-ish to it. It's kind of halfway between ALGOL 60 and Pascal, and they had the Control-C problem. And they did a complete hack to make it work.
So did I.
And it's a complete hack, it worked. I remember learning this and having the operating system listing and was being shown where it was, and it's sort of like the one little bit where assembler appeared in Burroughs code. Burroughs then rewrote its version of ALGOL into a new thing it called Noop to fix that, so that they could handle that in high-level languages. So it was a problem, but Arpanet wasn't it, and Arpa per se was very interested in using higher-level languages. It did not do a lot of research into them. It did not invest in them heavily.
That's fascinating. Thank you.
We're getting close to the end, so I think this will have to be the last question. Ian Moffat asks about the some of the work at NPL. Ian Moffat, would you like to put your question?
Yes, I'd be interested. I know Donald Davis's team were working on packet switching from, I think, about 1965 or 66 through to practical demonstrations around 1970. How much the early ARPA people were aware of that and kind of took it on board?
Completely. They're very aware of it. There are two sets of papers, one from NPL, and then RAND Corporation did some papers pretty much simultaneously on the same subject. The ARPA people were very aware of it. The leaders of ARPA traveled both to NPL and RAND to see what they had. RAND had very little in the way of working software, had a very worked out design, but very little. NPL had working software. And that, as much as anything, convinced Larry Roberts that he wanted to see if he could do a network at scale.
Thank you.
Can I now invite Doran just to say a final word of thanks to David for what's been a fascinating afternoon. Doran, would you like to offer
David,
a vote of thanks?
Thank you hugely. That was absolutely fantastic to get an insider view of what was going on. What it set going was a huge pile of thoughts about to what extent you thought existing conventional histories of the internet were either misleading or incomplete. I mean, we've got a story here which goes right behind the scenes. I was wondering if one approached the whole scheme from afresh and try to go to existing literature without access to people who are actually involved, what sort of impression would you get? I mean, sorry, I'm abusing my position here by asking questions. But how adequate is the current documentation in the history of internet if one tried to actually get to grips with what was happening?
You know, the current internet literature has a lot of good stuff in it. And, you know, Janet Abate's book is still the outline for, you know, sort of what does it. And that's a 99 book, 99. Khan's book on internet standards is very good. What I think is different to me and what's important to me, and, you know, has been true of all my writing, and especially, I mean, I can kind of describe it in terms of my book. You know, my main book is about groups of people who computed by hand. And I remember when I started working on that, pitching that to one of the computer historians, and you could sort of hear his eyes roll back in his mind, going, that's going to be the dullest thing possible. And it could easily be. You could say, well, there was this group, and then there was that group, and then there was another group, and there were these groups. And what really interested me was the problems they were solving and why they were the solution to a problem. How getting a group of people together to compute was a solution, and why those groups didn't get replaced by electronic computers, because they largely were not. And I think it's the same thing here, that the context for internet is far more interesting to me than you know, I'm going down the wrong track. The context is very interesting to me, and in particular, how the two go back and forth. To me, Arpanet is an example of a story of how academic computer science established itself. And its story is the end of a roughly decade-long period of getting, in the United States, academic computer science, plugging it into a certain number of groups in the UK and France, and setting up these things. And this technology links it. It provides an interesting set of problems that are solvable, that are not numerical analysis, and are not AI, which I think is important because AI has the problem of always overreaching and overpromising. These were problems that needed to be done and solved, and led not only to networking, but to distributed processing and a whole bunch of other things. And that context, I think, is badly explored. And one of the ways I can describe it is I go to used to, back when we could do this, a monthly meeting of entrepreneurs, of tech entrepreneurs in Washington. We have dinner in a Chinese restaurant, had dinner. It's been a year now since we've met. and talk about issues in science and business and technology. And we had this author who is a fairly well-known guy from the Wall Street Journal. And he wrote a book that was somewhat interesting in its own right, but it had a chapter on how business converted a defense technology into, which was to say Arpanet, into a commercial technology against the wishes of the Defense Department. And I sort of put up his hand and said, "What's your source on that?" He goes, "Well, everyone knows this." And I said, "Well, two thoughts. I've seen the documents and I've seen nothing that justifies that statement at all. My argument is that they were building a general purpose networking technology that they wanted used everywhere. I can produce congressional testimony to that fact by the ARPA leaders, where they said, this is what we're doing. General purpose network, plug it into any problem. It will work for anything. Commercial, military, secret, public, doesn't matter." And I can also get on the phone in 30 seconds, the lead of the project, who will tell you the same thing. And he dismissed it completely. "Everyone knows this," he says. "You don't have the story right." And it seems to me that the engineering process is a fascinating process that involves management and technology and the general public and governance, and a lot of engineers trying to make all that stuff work together for them to solve a problem. And it seems to me that the internet story, which is told primarily from a certain amount of technological innovation and then leaps to a certain amount of government control, misses the full scale of the problems that were solved, the forces that were brought into it, and how this ultimately was the solution to a series of problems that the world was facing. And that's, to me, the part of the literature that needs to be developed, and that's in many ways one of the intellectual reason of why I'm looking at this problem.
Wow, thanks very much. When can we look forward to putting us right?
We'll see. Doran, you have been down this path before, and there are things that, this talk to me is very important because it helps clarify some of these ideas in ways that I hadn't been thinking about before. And it will come in time.
David, for us, it was mind-boggling to see behind the scenes because there was material there that I didn't know existed and didn't even know that those issues have been addressed. So it's absolutely fantastic. I think you can tell by the questions and by the interest of all the participants of just how well appreciated it was. So thanks hugely. Terrific presentation. Thanks a lot.
Well, thank you, Doran. It was so good to see you, and good to see you all. And if there's anything I can do, if there are further questions, Doran knows how to get in front of me. Roger does, and I'm glad to respond to anything.
Thanks very much indeed.
Thanks to everybody.
Thank you.
Cheers.
Thank you.
Bye.
Bye.
Stay safe.
And thanks.